And so Liz is a recent civil engineering MASC graduate at U of T, and she's passionate about sustainability, building science, and computational design. And so we're glad to have you here. And you're welcome to share your screen whenever you would like.
Yeah, let me try. Yeah. So, hi everybody. Once again, I am Lizeth Rivera, and today I will present a summary of what was my research work. So it is titled Implications of Passive Energy Efficiency Measures on Life Cycle Greenhouse Gas Emissions. So let's begin. Why should we care about buildings? Well, the thing is that the construction and operation of buildings is responsible for about 40% of anthropogenic CO2 emissions. And what is more concerning is that this industry is in a continuous growth with no signs of slowing down. In fact, the world is expected to build the equivalent of a Paris every single week for the following 40 years. And therefore, there is a need for reducing greenhouse gas emissions in this sector. So in a building, greenhouse gas emissions are typically divided into embodied and operational emissions. And as you can see in this pie chart, operational emissions typically comprise the major portion of total emissions. And this is one of the reasons why most of the efforts has been focused on improving the operational performance of buildings. Some of the strategies to do so are called passive energy efficiency measures. An example of these measures is, for instance, adding more layers of glass to the windows or adding more insulation to the walls. The problem is that this increase in material quantities can also result in more embodied emissions. And these trade-offs between embodied and operational emissions might be offsetting any apparent emission reductions, generating counterproductive results. So to evaluate this trade-off, researchers have proposed strategies that combine life cycle assessment and energy simulation. However, there are some gaps and limitations in current work. So first, we couldn't find studies done in North America, just in Europe and Asia. Second, we couldn't find studies done for high-rise buildings, just for low and mid-rise. Third, we noticed that previous studies have evaluated a limited number of alternatives, which also limits the application of the results. And fourth, and the most important one, we found that previous studies usually consider parameters such as weather and electricity grid as invariable conditions throughout the service life of the building. And this neglection of environmental, technological, and policy changes that might occur in the future might be producing misleading results. So the objective of my research was to inform early stage decisions related to building envelope design with the aim of net greenhouse gas emission reductions. And to do so, we determined the implications of envelope-related passive energy efficiency measures on life cycle greenhouse gas emissions, considering first, the Toronto's condition for high rises, second, a broader number of design alternatives, and third, future environmental and technological changes. So how did we do it? So in simple terms, what we did was first model on a 3D environment, three case studies. Second, we created multiple variations of those buildings by applying different levels of passive energy efficiency measures. So for instance, changing the window to wall ratio or changing the insulation material, as you can see in this animation. Then we conducted energy simulation and life cycle assessment for every single variation. And to automate this process, we use a visual programming software, Grasshopper. So for the design variables, we propose 56 type of walls, 6 windows, 12 roofs, assemblies, and window-to-wall ratios, resulting in more than 16,000 envelope variants. These changes were done changing the insulation material, the insulation thickness, the number of glass layers, and the frame material of the windows. Lastly, we consider possible changes in climate and energy sources by using projected weather and projected electricity needs. So now let's move to the results. So this is a sample of the results. Here we have the global warming intensity over 50 years. Here we have the continuous insulation thickness, and these are different wall types. So first, we can see that for most wall types, every time the insulation is increased, the global warming intensity decreases, which is what is normally expected. But for these two wall types, something different happens. There is not significant reduction for improving the insulation, and in fact, you can see a slight increment on the emissions. And what these two wall types have in common is that they have SPS as continuous insulation, which is a carbon-intensive material. Just comparing SPS with EPS, SPS is more than 13 times more carbon-intensive than EPS, so the addition of this material considerably increases the embodied emissions, intensifying the trade-offs. And this behavior is repeated regardless of the window type used. But let's put these results in a little bit more in perspective so we can see like what is the impact of the results. So let's take building one, and let's say that we have this type of wall, which is a concrete wall with SPS as insulation. And let's say that we want to increase the insulation from 1 inch to 6 inches. So if we were looking only at the operation, which is the business as usual approach, well, the results are great. After 50 years, you will save 1.5 kilotons of CO2 emissions. But if we consider both embodied and operational emissions, well, you won't save anything. And in fact, you could increase about 0.5 kilotons of CO2 emissions. And this is why we must include embodied emissions into the decision-making process. Otherwise, we can implement something that looks great, but that at the end is worse than actually doing nothing. So now, more than the specific conclusions of this research, I would like to share some lessons. These two lessons: first, always question the business as usual approach. And second, design not only for the present, but also for the future. And these were the sponsors of this research, and thank you so much.